board, and then see the tool that gives this information for a vector field, that is the divergence of a vector field. Divergence of vector field. Let us denote vector field as A bar. Mathematically, a divergence of vector field is represented as del bar dot A bar, and we know del bar as dou by dou x cap in Cartesian coordinate system plus dou by dou y cap plus dou by dou z cap, and A bar as ax x cap plus ay y cap plus az z cap. So what will be del dot A? It is a dot product of two vectors, right? So what is del dot A? Multiply the corresponding components, add all of them. So it is a dou ax by dou x plus dou ay by dou y plus dou az by dou z. And you see, since the dot product of two vectors, the result is a scalar quantity. So the divergence of a vector field is a scalar field. Note, important point. And also do remember that you can't apply divergence to a scalar field. Why? If you apply divergence to a scalar field, then this becomes del dot f, right? And can you apply dot product to a scalar quantity? No. I told you that dot product and cross product can be applied only to two vectors, and you can't apply it to a scalar quantity. Similarly, the gradient of a scalar field, gradient can be applied only to a scalar field, because you remember what was del f? The gradient of a scalar field is del f, right? Del multiplied by f. Can you apply gradient to a vector field? No. If you substitute f with a bar, it would be like del bar multiplied by a bar, and you can't multiply del bar with a bar just like that. Multiplication of two vectors means either dot product or cross product. So mathematically also we can prove that gradient cannot be applied to a vector field. That means gradient is not the appropriate tool which will give you the information about the variation of the vector field with respect to space. So gradient only talks about scalar field. Similarly, divergence and curl, they talk about the variation of the vector field with respect to space. They cannot give you the information about how the scalar field varies with respect to space. And the name divergence indicates that there is energy flow out of the surface, or there is some energy protruding from various points in the surface, or the power flow out of the surface, right? So the divergence mainly relates to the rate at which the quantity that is referred flows out of the surface. Okay, so the divergence of the vector field, you know, it's a scalar field, and it gives you the rate at which the considered quantity, whether it is energy or power, that protrudes out of the surface, and it is always a scalar. It always results in a scalar quantity. Similarly, the other tool which describes vector field in a better way is the curl of vector field A bar. So mathematically, curl of vector field is represented as del cross A. And can you apply curl to a scalar field? No, you can't apply curl to a scalar field, because when you substitute A bar with F, it's like taking the cross product with a scalar quantity, and that we know it is not possible. And mathematically, how do you find out curl of vector field? Del cross A can be found out using the determinant form. Considering del bar and A bar in Cartesian, having their Cartesian form, del cross A is equal to determinant of x cap, y cap, z cap, dou by dou x, dou by dou y, dou by dou z, ax, ay, az. One of the simpler ways of understanding the curl of vector field is curl actually gives you the angular velocity at that point in the field. The name itself says curl, right? So when you say curl, it deals with the rotational property of the field. So you can consider a field as a rotational field or irrotational field based on the value of the curl of the vector field at that point in the field. So we will soon see in electrostatics the various types of fields, the nature of the fields, either is rotational property of the field or circulatory nature of the field or irrotational property or non-circulatory nature of the field. So whether it is a rotational or irrotational field, that information is given by the curl of the vector field A bar. So in short, we could say that when you take the curl of vector field, that means you are trying to find out the angular velocity at that point in the field, because curl will give you a vector quantity, right? That means it has got both magnitude and direction. And in the examination, if he asks you to find out the angular velocity at some point, say 1 comma 2 comma 3, and you see in the options that they are only magnitudes, that means he is expecting you to find out the magnitude of del cross A and see and select whichever is the appropriate one. Okay, and if he gives vector as in the options, then he is expecting you to just solve for del cross A and give the answer. So you have to understand the the thoughts of the question paper setter in such kind of problems. Okay, so but because you know that it is a vector, it has both magnitude and direction, sometimes you may explicitly ask, otherwise you have to understand the kind of question that is asked and choose the correct answer appropriately. Okay, so these three are very important concepts: gradient, divergence and curl. Gradient is associated with scalar field and divergence and curl associated with vector fields. And we have discussed gradient, divergence and curl only for one coordinate system, that is Cartesian coordinate system, right? That's because it is simple to understand. That doesn't mean that you can't describe gradient, divergence and curl in other coordinate systems. So what I'll do is I'll give you a table which contains the formulae for gradient, divergence and curl, the generalized formulae for gradient, divergence and curl in all the three coordinate systems, that is Cartesian, cylindrical and spherical coordinate systems. You can expect a simple 1 mark question on this. Let's erase the board. Coordinate systems. The three coordinate systems: Cartesian, cylindrical, spherical. Let me take some variables u1, u2, u3, h1, h2, h3, e1 cap, e2 cap, e3 cap. For Cartesian coordinate system, this is x, y, z, cylindrical r, phi, z, spherical r, theta, phi. h1, h2, h3 would be 1, 1, 1, 1 r1, 1 r sin theta. And e1 cap, e2 cap, e3 cap would be x cap, y cap, z cap, r cap, phi cap, z cap, r cap, theta cap, phi cap. So the gradient of a scalar field del f can be found out as dou f by dou u1 e1 cap, dou f by dou u2 e2 cap, plus dou f by dou u3 e3 cap. Sorry, this is 1 r sin theta, not just sin theta. Then del dot A, divergence of vector field, can be found out as dou by dou u1 of a1 h2 h3 plus dou by dou u2 of a2 h1 h3 plus dou by dou u3 of a3 h1 h2 by h1 h2 h3. Del cross A can be found out as determinant of E1 cap by h2 h3, E2 cap by h1 h3, E3 cap by h1 h2, dou by dou u1, dou by dou u2, dou by dou u3. A1 h1, A2 h2, A3 h3. So you could use these three formulae to find out the gradient, divergence and curl in any of the three coordinate systems.